Hello. All right. Hello, everyone. Just give me a couple of minutes. I'll begin. Dun, dun, dun. Bin is working. Okay, yes, let's begin. Any questions? How's everyone? Supposed to be the last lecture, I believe. Upload the PDF notes on the Google Drive. I will do that. Sorry about that. Anything else? Nope. How are the projects coming along? Oh, by the way, there were a couple of emails that I received that I wanted to address. There were several questions being asked on the email. One of them was about the word limit and the page length. If your project goes beyond 5 pages, that's fine. It shouldn't go too far beyond. I'm not putting a cap on it. I don't think you would need too many pages. I think you can just put a reasonable amount of your research in 5 pages, but if you think more is necessary, then go for it. I will not stop you, but the less the better. You can say things minimally as possible, right? Okay, but you won't be penalized if your report is like 6-7 pages. That's fine. That was one of the questions. The other question was, so some students sent me their projects for review. I won't be reviewing any projects until the deadline, and then I'll just look them over and check them. There's no, like, I can't tell you if it's fine, if it's not fine, if it's whatever. Like, do your best and then just submit it, because a review is a never-ending process that I don't want to really start. Okay, so, and I'll reply to those emails individually as well. Sure, just put it in the Dropbox. Okay, alright, so if there's nothing else, we can begin. And so let's see, let's talk a bit about some different things. And I'm going to just, for today, I'm just going to go over, since we can't really cover much in graph theory, then my idea is that we just cover a few things in not that cover a few things in detail. Instead of doing that, I will just give you an overview of what kinds of questions and what kind of notations are involved in a graph, right? Okay, so let's see, where did we end the class? So we talked about the handshaking theorem and the number of vertices of odd degree, that we knew that there are an even number of vertices that have odd degree. And so let's talk a little bit more about some notation. So the first, another definition is, so there's a definition, so definition, let's make this black, and okay, so the definition of adjacency, right? And so in a directed graph, if there is an edge from u, vertex u to vertex to v, then we say, firstly we say u is adjacent to v. We also say v is adjacent from u, right? And so these two vertices are basically called adjacent to each other. Okay, and so let's say you have one vertex u and there is an edge going to another vertex v, so u and v, right? Okay, the next thing is, in a directed graph, sorry about that. In a directed graph, we have two notions. The first notion is that of the in degree of a vertex in a directed graph. By the way, in this one, in this notation, we call u the initial vertex, and we call v the terminal vertex. So we have two other notions. The first notion is that of in degree, right? which is the number of edges, the in degree of V is the number of edges that have V as the terminal vertex, which means, for example, if you have a graph in which there are, let's say, 3 edges coming to V, then we say that the in degree of V is 3, which means we write it something like this: degree minus of V is equals to 3, right? And the out degree is a similar concept. You can guess what it means. The out degree is basically the blah 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 of V is the number of edges that have V as the initial. So same definition as above, but except that in place of terminal vertex, these edges will have V as the initial vertex, right? So now if there's like 2 other edges that are going out of V, then the out degree, then the degree plus, which is the out degree. This is the notation for out degree, this is the notation for in degree. So the out degree of V is 2, right? So there are 2 edges going out of V and 3 edges coming into V, right? Any questions? Is that clear? Okay. And so, where was I? Okay. Yeah. Okay. And so if that's clear, then we have a simple relationship that we can just codify. It's a theorem which says, in a directed graph, let GVE be a directed graph, then we have the degree, the sum of all the vertices, all the degrees, the in degrees. If you take the sum that you're taking with over all vertices, you're counting their in degrees, or you take the sum and you count their count all the total out degrees. So for example, V1, V2, V3, let's suppose I have this simple graph, right? So this is 1 edge, 2 edge, 3 edge, 4 edge, V1, V2, V3, V4. Let's say this is the graph, and right. And so if I do that, notice that if I start taking the in degrees of all the vertices, so for V1 the in degree is 1 because there's only 1 coming in. So let's say I'm doing the in degrees right now. So in degree is 1, in degree for V2 is 2, in degree for V3 is 0, and in degree for V4 is 1. So if I sum them up, I get 4. For the out degrees, if I start counting them, for V1 the out degree is 1 because there's 1 edge going out. For 2 it's 0. So now if I do the out degrees, this is 1, this is 0. For V3 it's 2 because there are 2 edges going out, and for V4 it's 1. So if I again add them up, it's equals to 4. And notice that it's the same number as the number of edges you have, and that's a trivial thing, right? So it's just equals to the cardinality of it, that is the number of edges in your directed graph, right? And that's easy to see, because if you have an edge, if there exists, it's a simple argument. If there exists an edge, it will contribute +1 to the in degree and out degree. So in degree of some Vi and degree out to some vj. It can be the same vertex as well if it's a loop that's coming back into itself, but if it's going out into 2, so it will contribute +1 to both. So it will contribute +1 to the in degree of some vertex and the out degree of some other vertex, right? Or maybe even the same vertex. And so this is equals to 4, which is the number of edges, right? So each edge will contribute once to this and once to this, which means the total number of edges is going to be the same as the total number of out degrees and total number of in degrees. Okay. Any confusion? Is that clear? If that's clear, then let's talk about some graph. Okay. So let's talk about some simple graphs. The first example is complete graphs, right? And in complete graphs, the idea is simple, that if you have basically one edge connecting each pair of distinct, excuse me, so there's one edge connecting each pair of distinct vertices. So for example, if I have 3 vertices, so one vertex, other vertex, third vertex, if I connect each pair with just one, like we call this k3, right? Similarly, if I have 4 vertices and I draw just one graph with one edge between 2 pairs of distinct vertices, so I'll start with this vertex, draw one edge outwards towards each of the other ones, then I start with this one exists already, so I can draw this edge and this edge, then I go to this one, it's already connected to this one, already connected to this one, so I can just connect it to this one, and so this is K4. This is a complete graph of 4 vertices, right? Okay. Alright, you have other graphs as well which are called cycles, and cycles are easy to see. Cycles just start off from, you can think of them as starting off from one vertex to another vertex and then continuing to the third vertex and then finally connecting back. So it's basically, there's an edge connecting V1, so if I label V1, V2, V3, there's an edge connecting V1, V2, V2, V3 and up until Vn and Vn V1 again, back itself, right? So that's a cycle. So for example, if I have 4 edges, then I start from the first one connected to the second one, then second to the third, third to the fourth, and fourth to the fifth. So this is C1, I think. Do they use that notation? Yeah, C1, sorry, this is C3 actually. So this is C3, this is C4, right? Any confusions? Is that clear? Okay, so you can have different kinds of graphs, and at this point I'm going to okay, let me just talk about one more kind of graph before I move into a general discussion. So there's one kind of graph which is important, which is called a bipartite graph, and this graph is basically something like this. It's called a bipartite graph if you can how do I state this? If you can make a partition, make a disjoint partition of V, so this is my set of vertices, right, into 2 subsets, V1 and V2, such that any edge in G, so I have a graph G, any edge in G connects a vertex in V1 to a vertex in V2. For example, let's say you have some edges and you can separate them something like this. So V1 So this is V1. Let's say this is my set of V1 vertices and my set of V2 vertices. And if I can make and if my graph is such that I can make this separation, and only if there are edges that connect vertices in these two, so something like this, like this, like this, but there shouldn't be any vertices, any edges that connect two vertices from this graph, right? So there should be no edge that connects some vertex in V1 to another vertex in V1. So this edge, something like this, is not allowed. So it should only connect some vertex in V1 to some vertex in V2. And some graphs are bipartite, they can be separated like that. Some graphs are not bipartite. For example, let's think of a graph, for example, and see whether it's bipartite or not. Right? So for example, if I draw a simple little graph like this, let's say 1, 2, 3, 4 of just 4 vertices, is this a bipartite graph? Can I separate it into two distinct parts such that there's only one set, such where there's only edges from one set to another set? Is that possible? So cycles, we're not talking about Kibble-Then cycles are not directed graphs, so there's no notion of in degree and out degree. A cycle is an undirected graph. If there are no arrows, then it's an undirected graph. Okay, so if I try to make, for this one, if I try to separate them into parts like this, you can see that there is an edge connecting these two and there's an edge connecting these two. So that's not a correct bipartition. If I connect it like this and like this, if I call this set V1, V2, again there is an edge connecting vertices in V1 and vertices in V2. The only trivial way it might be possible if you just make a bipartition of one vertex, but that's a trivial partition that you can do in any graph, right? So that's not useful. So this is not, these are not bipartitions. Not bipartitions. Okay? What do you mean about diagonal edges? Okay, so we deleted that. Okay. Any confusion so far? So these are bipartite graphs, and you can also have something called complete bipartite graphs. So let's see what complete bipartite graphs look like. So for example, if I have two vertices in my first set, so let's say these are V1 vertices and these are V2 vertices. To make this graph complete, a complete graph should have edges between two distinct vertices, right? But in a bipartite graph, you're not allowed to have an edge over here and an edge between vertices in this set. So the only way you can complete it in the way you complete edges is to make an edge between these two, and these two, and then these two, and these two. And you can't draw any other edges between any other two distinct vertices, right? So this is called a complete bipartite graph of called K23, such that it's complete. K symbolizes that it's complete. 2, 3 symbolizes that it's a bipartition where one set contains two vertices and the other set contains three vertices, right? So for example, if I were to draw a graph K33, that means I put 3 vertices in one set, 3 vertices in another set, and then just draw the possible vertices, the possible edges that are allowed. So from here to here, from here to here, and this edge is allowed, this edge is allowed, this edge is allowed, and then this one, and this one, and that's all. That's the K33 graph. Okay. All right. So at this point, I want to stop because there's lots of things we can talk about. So let me just give you some idea of the different kinds of things that you can have, right? So what kinds of things can you do with graph? Another notion that you have is that of subgraphs, where basically you take some, so a subgraph would be, so H, W, F is a subgraph of G, VE, such that W is a subset of V and F is a subset of E. So for example, if you have a graph and you take some of the vertices and some of the edges and exclude the rest, then that's a subgraph of the previous graph. So you can draw new graphs from old graphs. So for example, if I take this graph and I just take this vertex, then for example I just take this vertex from the first one and only these two from the second one, then this subgraph looks like this, right? So this is a subgraph of this graph K33, right? Because there are some edges, some vertices from it and some edges from it. Okay. What else? You can also have the notion of isomorphism, which is a notion that allows you to check. It allows you to check if some graphs are, if one graph is equivalent, if one graph is equivalent to another. For example, let's say I've drawn a graph like this. Let's say I draw a graph like this and another graph like this. Oops. Both of these graphs are isomorphic to each other, and the idea of isomorphism is you can create a one-to-one map from, there is a one-to-one map from the vertices to the vertices of this. So from V1 to V2 there's a one-to-one map, and from E1 to E2 there's a one-to-one map. So you can identify, basically it's a relabeling. When it's an algebraic isomorphism, we just say that it's a relabeling of the variables. In this case it's sort of a reshaping of the graph, right? So you're just drawing the same graph but in a different way. So you can identify this edge with this edge, this edge with this edge, this edge with this edge, and this edge with this edge. So if you identify the edges accordingly and you identify the vertices accordingly as well, then you know that this is essentially the same graph. There's no difference between them other than the way I've represented them visually, right? That's another question that you can ask. I've already talked to you about adjacency lists. There are adjacency matrix. There are other way of representing graphs as well. There's an adjacency matrix that I've already talked to you about. Other than that, there's also things called adjacency lists and incidence matrix, right? Okay, so what kind of questions can you ask about graphs, right? So here's some questions that in the coming sections, if you want to read the sections, and I know some of you are doing projects on graphs, so these are some questions that you might already be dealing with. And so the idea is there are several questions. Once you have this basic understanding of the notation, of the notions involved and what graphs are like, you can ask several questions about them. You can ask questions about them. How connected is my graph? right? And you will ask this question in the context of, let's say you're doing an application, you've made a graph about a computer network, and when you ask how connected is my computer network, maybe you're interested in knowing that if one of your servers goes down, will my network still be running? Because if it's a poorly connected network and it's connected in such a way that just one server fails and your entire network stops working, then it's not a very well connected graph, right? So that's something that you might be thinking about from the lens of a computer network, or maybe you're thinking about it from a sense of train stations. So for example, let's say I have a badly connected transportation network. Let's suppose these are my different stations, and so let's say these are the connections between. So there's a central station, right, to which every other station is connecting. Now here's a problem. If this station stops working, for example, if I just remove this vertex, there's no other connections. There's no other connections possible between these other stations, which means your transportation network fails completely, right? So to avoid that, you should have perhaps, if it's important for you to have a connection between these two stations and these two stations, so even when this vertex fails, you know that, okay, I can still have commute between these two stations and I can still have commute between these two stations, although I can't commute between these two different regions, right? So those are questions that you might be interested in when you're talking about how connected your graph is, right? And there's also the notion of connected components, right? Connected components. So when I say connected components, we're basically saying, okay, let's say when this part fails, then still I have one connected component here and another connected component here. Initially, the entire thing was connected, so it was only just one connected component, right? So that's an idea, a mathematical idea that you introduce to understand how connected your graph might be, right? And you can also ask a question about different paths, right? So is there, and this is a notion that is very close to the idea of connectedness, which is that is there a path between V1 to Vi to Vj? For example, in my initial network, let's suppose this is my network, Control C, Control V. So let's say this is one of my stations and this is one of my transportation networks. So let's say in one of them this fails, right? So now the question is there a path between Vi to Vj? So let's suppose this is V1, V2, V3, V4. So is there a path between V1 to V4? Yes, you can start from V1, you can go to this station, let's call this V5, and then you can go to this. So these two are connected and these two are connected, right? So that's the idea of having a path. But in this one, between V1 and V4, there's no path between V1 and V4. So V1 and V4 are not really connected. So you can talk about the connectedness of vertices, you can also talk about the connectedness of entire graphs, right? Okay. What else can you talk about in graphs? Another question that you can ask, this is a very familiar puzzle, right? So another question that you can ask is, can I start from a vertex and traverse the graph in such a way that I only traverse each edge once and return. And do you have to return? Return to my, only traverse each edge exactly once. So exactly once and return to my initial vertex, right? And so if you recall, this is related to one of the puzzles that we do. So you must have seen some puzzle like this in high school, right? And so the idea is, can you start from one vertex and return to the same vertex? And for this one, it's very easy. So you can go from this vertex to this, and you're back, right? So such a path exists for it. But what about when you have a graph like this? Can you still start from one vertex and return to it? So, right? So if I start from here, then go there, here, and back, I can't come back to this vertex, right? And so for this one, that doesn't exist. Another question that you can ask is a similar question, right? Can I start from a vertex and traverse the graph in such a way such that I only visit each vertex exactly once, right? And so that's another question that you can ask about graphs, right? So, and again, in this one you want to return to my initial vertex, right? And so these questions are very similar. One of them has a very easy answer, the other of them is very difficult to answer, right? They're very similar questions, but with very different answers. Okay, and I think some of you are also doing a project about the Königsberg bridge problem, so that would be interesting to see how you answer this question, right? And so this is closely related to the idea of Euler circuits and Hamilton circuits and Euler paths and so on and so forth, right? Okay, what else? You can also ask a question about shortest paths, right? If in a weighted graph, in a weighted graph, so firstly the question is, what's a weighted graph, right? So before I introduce the question, I should introduce what a weighted graph is. So a weighted graph is simply with each edge there is some weight associated. So for example, let's say some weight W1, W2, W3, and as an example you can think of these as an airline. So this is an airport, this is an airport, and this is an airport, and the weights that are assigned are perhaps cost of flying from this airport to this airport and this airport to this airport. And so the question is, if I want to fly from V1 to V2, which you will want the cheapest route, right? So if you will compare the cost of W1 with W2 plus W3, right? And so you would want to fly the cheapest from V1 to V2. Well, if affordability is an issue for you, otherwise if you're rich then you're not going to worry about it, then you might just take W1 because it's the shortest one. But the idea is, if you're worried about the weights and you want the route with the smallest total weight, then the question is, I can ask in a weighted graph, what is the shortest route or shortest path from Vi to Vj, right? And so shortest, let me just clarify one more. Shortest doesn't mean the minimum number of edges. That is different. Minimum number of edges is not the same as this shortest idea. The idea is that by shortest I mean the smallest total weight of the path, right? So if you sum all of W1, W2, W3, blah blah blah. Yes, this is used in the traveling salesperson problem, right? So these ideas are used in the traveling salesperson of having a shortest path. So this is important. Even the previous idea is used in the traveling salesman person, right? So, and the traveling salesperson problem, those of you who are doing a project on it should know that it's not an easy problem to answer. It's you have to consider each and every possible route And so there are some examples that are easy to do, but for complicated graphs, you have to check a lot of possibilities, right? So that's another question that you can ask about graphs. Okay, what else? Then there's the idea of planar graphs, right? The idea of planar graphs. Can I draw my graph without any crossings, right? So for example, if I have a graph like this, let's say something like this, can I redraw this without having any crossing? So already this has no crossing, right? But let's say I put another edge here. Can I redraw this without having this crossing? Because I don't want any paths to cross, right? And that's the idea of a planar graph, right? A planar graph can be drawn without any edge crossings, right? And so of course I can, if I redraw this something like this, if I keep every edge as it is, and let's say I drew an edge, now I need to connect this edge to this vertex to this vertex, I can simply go outside the box and connect it like this. And so now I have no crossings, right? And so this is a planar graph because it can be drawn in a plane without any crossings, right? So let's say, what about this one? Let's say if I have a K33 graph, right? Let's say something like this. So I have K33. Can I draw this without any crossings? Is this a planar graph? What about this one? If you remember a cube, something like this, can I draw this without any path crossing, right? So at this point, you can see that this is going to cross with this, and this other one is going to cross with this. Can I redraw this without any is this a planar graph, right? And so that's another question that you can ask about graphs. There's also the idea of a graph coloring. Some of you are probably doing that as well. And so a graph coloring is basically related to the idea of coloring, which is question, which is, can you color? So for example, if you have a map, can you color a map? Can you color a map with, let's say, with n colors, with no two regions having the same color, right? And that same color. And this problem can also be tackled using graph, right? So a map coloring problem can be converted into a graph coloring problem. So you just take a map. So let's say you have this map with some regions in it. Let's say these are some of the regions, blah blah blah. And so let's say A, B, C, D, E, F, G. And instead of thinking about it like a map, you can draw a corresponding graph to it. So you can represent this idea using a graph in which you can label you can draw a vertex for each of the regions. So this is A, B, C, D, E, F, G. So A, B, C, D, E, F, G. And instead of drawing it like a map, you can draw edges between any two regions which are connected with, which are adjacent to each other. So A and B are adjacent, so I will draw a edge here. A and D have a common region, A and C seem to have a common region, B and C seem to have a common region, D and C, D and E, E and C, D and F, F and E, D and G, and G and F. So this is a corresponding graph. So you've taken the map coloring problem into a graph coloring problem. So if you can, now you can state the problem. Instead of asking, can I color them with 4 colors without the same color with adjacent regions having the same color, the question is, can I color the vertices with no 2 adjacent vertices having the same color, right? So for example, if I label this red, then I can't have any of B, C or D as red, right? But I can have E as red, right? So essentially you've taken a map coloring problem and converted it into a graph coloring problem. And so this is only a few. There's also some related questions that you can ask, which is how do I traverse the entire graph, right? And so there are algorithms that are written to traverse entire graphs. So the point is that there's lots and lots of things that you can do with graphs. We of course have run out of time, and there's only an overview that I can give you. If you're interested in it, some of you are of course doing some projects in them, so you can explore these things on your own. But the point is there's a rich literature on graphs, and they have, especially for computer science students, there's a wide variety of applications that you can look into. And most of these problems, if you explore these will make you better computer science students. They're really smart solutions. They're approached in a very smart way, so I would recommend that you look into graph theory. And that's all. There's really nothing more that I can cover, any meaningful material that I can cover in this time. So if you have any questions, let me know. That's your entire. Is this the last lecture? I was considering that if I should take another, but you know what, let's just end this here and call it a day. No ifs, that's it. I think this is enough material to be covered. Are all these questions included? No, of course not. I've not even discussed these questions. If I've not taught them to you, I can't expect you to know them. These questions are just mentioned so that you know what kind of stuff is, what kind of ideas are present in graph theory, and if you are interested in them, you can go explore them on your own. How are the projects coming along? How are your other classes going? Are they going that bad, Tanya? Or is this sadness about the course ending? They're there. Just waiting for them to end. The semester was way too long. Yeah. Okay, I don't think anyone else is sad about this course ending other than you, Danya. It's been a long semester, and with quite a few challenges. I can only imagine how you people are dealing with it. Projects 100. I hope I've not burdened you as much. I've tried to keep the workload as little as possible. I was going to do 5 assignments, and 2 exams, but now you have like 3 assignments and 1 project, and I don't know if what am I doing in the final. Kiblathan, honestly, I do agree that given the kind of project proposals that I got, I honestly am seriously considering keeping a project, for like a mandatory thing for my courses, because it really, I could see that you people were trying to research on your own and trying to learn on your own, and I don't think I could have, that kind of thing can't come from me forcefully telling you to learn something, right? Because if you don't find it interesting, then there's not really much you can do. But at least in the projects, you were being forced to go out and explore on your own and see what you're interested in. The assumption is, of course, that these were taken seriously and you went ahead and did your own research. And so I do believe for those of you who approached this project positively, I'm sure you must have learned much more than what I am able to teach you in a class. ओके नहीं बेटा, मैं तो जन्नती नहीं हूँ, मैं तो बाय डेफिनेशन जन्नती नहीं हूँ, तो इसका तो मैं anyway. Yeah, I personally think it's not a, yeah, Jannati, that's ek to, this label I would seriously not want, at least from IBA, because in IBA, if you're Jannati, then you're not really testing your students. But this semester, I really can't expect too much, even though I drew. Of course. These are weird times. I don't know what's the best way to deal with them. I personally do think that it's important to keep the students motivated and to keep the course as slightly challenging, and my definition of slightly challenging becomes more very challenging for the students, but I do think that that's important. So yeah. Not more than what I communicated to you before, which is I'm considering extending your reports. If I will go through your reports once I receive them for the midterm and see the kind of work that has been done, and then I might give you an option. No problem. I'm glad. I think that. Yeah, you're welcome. Anything else? खत्म करें फिर एंड करें सेशन. Okay. This is the last TM lecture for at least this semester. जी आपको सवाल पूछना है तो आप पूछ लें. Okay, Danya, you can do a Zoom conference for the office hours if you don't want the course to end. They're there. And you can attend my linear algebra lectures. I've not taken a linear algebra lecture for a while, so I'm gonna take some more, hopefully. Okay. Oh, you're welcome. No, you don't need to thank me. This is my job. Okay. All right. We will let Dania calm down, and if there's Anything else, let me know. Let's fade to black. Also, by the way, one last thing before I leave. You've all been nice about the lectures. Well, I'm guessing there's like 90 of you, but you've still there's always been like 8 to 10 students or sometimes to 15 students in the live lectures, and I know it must be difficult when you're staying at home. So I'm glad that you did attend the lectures, and there was this. This was not easy teaching from here, but this was of course a new experience for all of us, and we were learning and trying to make the best of the situations. Afnan, I honestly don't know what I'm doing, so I've thought of a couple of options. One option is that I'll just give you again another option about an assignment or a viva or a extension of your report. So I'm still considering my options. Once I've made up my mind, I'll just put a post on Piazza and let you all know. That's same response, Ashit. ओह, आज तो नए नए लोग सवाल पूछ रहे हैं. Report against final sounds nice. Yes, it sounds nice, but still we don't know कि finals का क्या हो रहा है. Maybe if the IBA tells us something that this is what you're supposed to do, then my hands would be tied. So I don't know. How many more classes to go? अच्छा, ये अब जाके इनको अगर कोई जवाब देना चाहें तो दे दें. Anyway, challenge. Okay, I'm going to end this now because I don't think there are any more questions. Are there? No, right? Thank you, everyone. Yes. Okay, thank you, everyone. Have a good day. Have a good end of semester. And enjoy your vacations however they look like at home. Bye. Again, no need to thank me. Bye.